Hello and welcome to another tutorial. So this time around we are going to be taking a look at algorithms in C++ and not actually building the algorithms but looking at the huge swath of algorithms that are already there. Now we won't be looking at all of them because otherwise that would be a probably 20-hour long video and that would be a little bit too much. But we're going to be taking a look at a bunch of ones that do a few key things. It allows us to do that quite easily, and that'll give us a bit of a sense of sort of the general structure of how they work. And I'll link you to a reference where you can find information on further algorithms that exist within there, so that you can look and see other ones if there's different ones that you want to use, how you would go about using them. So let's dive on in. So when we're talking about algorithms, in this particular case, we're talking about using them for processing data and for working with data, for finding information in it. It might be for modifying the data, it might be for querying it, different things like of that. So that's what we want to get up and running with this. So what we're going to do is firstly, we're going to set up a little bit of data. So I'm going to include vector. Now the nice thing with the standard algorithm setup is whether you are working with vectors, lists, other types of containers, the algorithms are largely container independent. They work as long as the container provides our standard iterators, it's going to be able to work with those algorithms, which makes it really handy. Means they're sort of container agnostic, which is great. So to bring in the algorithms, unsurprisingly, we include algorithm. So first thing I'm going to do is I'm going to just set up a vector with some data. Now, the particular data in this case doesn't really matter. I'm going to use integers, so in vector, and I'm going to just throw some data into this. So I want to just put a few different numbers in, just enough for us to have a few things to work with. So that's a few bits of data. That'll do the trick. So, okay. Some common things that we might want to do with this. And generally what the algorithm stuff replaces is things where we would normally go and write a loop to iterate over all of the data. So, okay, some common things might be retrieving the minimum and maximum values. So let's do that. So how that would look is, okay, well, I can go standard max element. Now you'll see it's asking for the first and last iterators. So iterators are a data structure that we can use in C++ for traversing data structures, for iterating over them. And they do make that a lot easier because algorithms can be designed to work with an iterator, and then it can work with any different type of container that supports those iterators. And by the same token, we can create a container that implements those iterators so that then algorithms can work with it. So first thing, we need to give it an iterator for where we want it to start. Now I'm going to give it the very beginning, but we could give it an iterator later on in the container if we want it. So it doesn't have to be at the beginning. In this case, I just want it to be. Then we give it an iterator for the final point to be able to be looking at. And in this case, I'm going to use the end point. Now, remember with iterators, end actually isn't the last element. End is not exactly, but kind of conceptually one beyond the last element. It's an invalid point. So, okay, we've given it the start and the end. Now, one of the things that we can do is we can actually give this. Now, for very simple data, this is generally just going to work like that. And we can run it, and we'll see what it does, but we'll see how we can also customize this in a moment. So I'm going to use auto because it makes it a little bit cleaner and neater for storing the data type, and also means if I change the container, I don't need to go and update this. So whenever I'm working with iterators, I usually incorporate it or ITER into the name just to make it clear. And what I want to do is, firstly, check that it actually found a max element. Now, for something like max, it's unlikely to fail, but just to be sure, I check that it's not equal to int vector end. And if it's not, then I can say, okay, maximum value is, and then we include value, which being an iterator, to get the actual value, we dereference it. So let's test that. So it comes back and it gives us 6. So for something like an integer, straightforward, can easily work exactly as we need there. Say it's a more complex type, or we wanted to do something really terrible and make max actually do the opposite of this. But mostly if it's a really complex type. What we can do is we can actually provide what's called a predicate. So a predicate, one of the ways that we can provide them is as a little function like this. And the idea is this is a little inline function that it essentially handles how you evaluate max. So what I would do in this case is we return LHS is less than RHS. Now we should get back the same result of 6, which we do. Now if we wanted to mess with this, we could do that, and then we get back 0. Obviously that's quite wrong, but we can do this. So, okay, this is handy if we had a custom data type there. So say we had a structure and we wanted to get the maximum element. We'd need to implement some means of comparing it, or we can set up a little predicate like this. So really handy. Now, unsurprisingly, as well as max element, there is also a min element. And again, not surprisingly, very little changes. So we update these. So mostly my renaming is just for actually making it make sense. So okay, we've updated the naming of things. Now the predicate, we haven't actually changed that. And we actually won't need to, because the predicate isn't specifically finding the min or the max. The predicate is actually answering the question of, does the left-hand side go before the right-hand side? That's what it's the question that it's actually answering in this case. So min and max, although it's using different functions here, they use the same predicate, which is really handy. So okay, min, max, that works. What if we wanted to find where something is in that vector? Well, what we can do is auto found value it. And we can do a standard and find if. So we can find something that matches a particular criteria. Again, we use our standard approach with int vector begin and end. And then again, I could give it, okay, let's ask it to find 6. And then we check, did it actually succeed? So if that's not equal to end, then what I want to do is I actually want to output where we found it. Found value at position, which we can get the position by doing standard distance from int vector begin to found value it. Now, standard distance is not going to be applicable in all cases. In something like this, where things are organized linearly, yes, it makes sense, but it won't necessarily be valid for every single container type. But when it is, really handy. So, okay, let's see what that does. So we've told it that we want it to search for 6, but if we run this, we actually get an error because this, we can see the particular output, we actually have to be providing a predicate for this particular version. So we again provide our predicate. In this case, what we're getting is the element. And all we do is we return if element is equal to the value we're searching for. So let's run that. And we can see, found the value at position 2, which makes sense. 0-based, so position 2 is the third entry in there, so that's good. What if we searched for something that doesn't exist? Well, just outputs nothing, because the result here was end, so it didn't pass this test. So, okay, we can find the minimum, we can find the maximum, we can search for particular things. Again, really handy if we're wanting to just be comparing stuff. Okay, what about if we're wanting to order stuff? And in particular, this is quite handy if we're wanting to order something where it's custom data or we're wanting to order it in a particular way. So what I'm going to do is we have standard sort. We give it our begin and we give it our end. Now, standard sort in this case is actually going to modify the data that we're providing to it, so it is modifying the container. And what we can do is we can give it, again, a predicate. And it's going to look very similar to what we've done before, where it's comparing two values. So again, we're returning which things go before the other thing in the sorting order. So we might want to sort ascending or descending. So I'm actually going to put an option here. Bool ascending, we'll say is true, and then I'm going to bring that in so we capture it. And I can actually just capture by value. We don't need to capture by reference in this case. So, okay, well, if it's ascending, then what I can do is I return true. LHS is less than right-hand side. Otherwise, LHS is greater than right-hand side. And then what I will do is I will output the sorted data. We have sorted data. And we just loop through the values. Oops. So used to C# at times. Always a challenge switching between the two. And then we just output. Now this is the value. So we're expecting this to be an ascending order, which if we've got our predicate right, we can see that it is. It also means if I change this to false, it should be reversed. And we can see that it is. So we've got a handy way of being able to do our sorting, and we can actually indicate ascending or descending, and it's just all in the one thing. And again, if this was a more complex type, we might be sorting structures, locations in the world, or might be a set of enemies that we're sorting. There's a lot of different things we could be sorting here, and being able to provide a predicate like this allows us to actually easily write our own custom solutions for how it orders that data. And in particular, there might be cases where you want to sort it one way, and then in another case sort it a different way, so really handy for those. So, okay, we've modified the data by sorting it. Let's start to do some further modifications. What if we want to actually replace particular elements in this? Well, unsurprisingly, there is an algorithm for that. So what we have is we have a standard replace. Now, we have different versions of this. I'm going to use the sort of more destructive one, the one that actually is going to modify the array. You do have ones that can actually give you a modified version of it. I'm going to do the destructive version. So we tell it where it's searching between all of our usual stuff that we normally do. And again, we provide a predicate for it, and it's a similar one to when we were doing a search, because what this predicate is answering is, should I modify this particular value? So, and we give it what we want it to replace it with, which will say 42. So there's a number of different things that we could be testing here. And yeah, with an integer, it's pretty simple, most of the tests we might be doing, but data structure could be much more complex. But for example, say I wanted to modify any value that is even. Then I could go, well, element modulus with 2, which if it's even, will be 0. And then I output that data again. So modified data, which we should expect to see a bunch of ones, and essentially anything in the sorted data that was an even number is replaced, or at least anything that has a modulus of 2 being 0, it's now being replaced. So, okay, really handy. We can swap out elements like of that. What if we want to remove only particular things that match a certain criteria? So we could also do that. So it's quite similar in many ways. We have a remove if, and we give it the begin and the end. Now, this behaves in a very particular way that's really, really easy to think, okay, yep, everything is fully working with this. And I'm going to actually show the problem before we actually look at what we do to fix it. So we're going to say that it should remove it if the element is 42. And then I'm just going to output the data. So this is our filtered data. So let's take a look and see what that looks like. Now we do see we're getting a warning, and we do notice the filtered data looks more than a little bit weird. Here we have 1 is there now twice, and rather than there being 4 of the 42s, there's 3 of them. And that's because remove doesn't actually remove the elements. What it does is it shuffles everything that isn't being removed to the beginning of the container, and then it returns an iterator that you can use for removing things. So it gives us back an iterator, and then what we can do is a int vector arrays from remove point it to int vector dot end. So remove is not actually doing a removal. It shuffles the things to be removed to the end and gives you an iterator that essentially says, cool, you can delete everything from this point to the actual end of the container, and that will trim off the data that you need. So if we run that now, we see we only get a single value back. So it's an easy trap to run into with these different remove functions, where it can seem like it's actually not working, but it is also sort of making changes, and it's very easy to run into that. So you would generally see a remove paired then with an arrays afterwards to clear out the data. So just something to be aware of with it. Okay, so we've seen things for finding min values, max values, for sorting stuff, for replacing, removing. So a lot of really handy ones there. We can also do, and it's useful just to sort of see a couple of other ones. What we can do is we can also, say we want to know how many things match a particular criteria. Well, we can do a count if, and same pattern that we use. So our begin, our end, and then we provide it again with our predicate. So in this case, I might want to count the number of things that are even. So %2, 0. And this is going to give us back auto count. So we can say cout num matching values is count, like that. So if we run that, num matching values is 4, which 1, 2, 3, and 4 match that test. So, okay, work straightforward with an integer. Let's set up a really basic struct as a alternate version of this. This is going to be our int holder. That, and we'll just give it a basic constructor like this. That's good. So I'm going to change this to int holder, and all of these get modified like that. Now a bunch of things are going to break. That's okay. We've got a few standard changes that will actually fix all of these. So these would be a const int holder, int holder ampersand LHS, and a const int holder ampersand RHS. So I'm just going to do that for any of the ones that use this. So not too much changes with our predicates. And really, the main thing is just going to be a little bit of renaming here. These ones, const int holder and for the element, so that's good. We'll just update all of these. Now that's going to cause a bunch of things to break and be grumpy, which is fine, because we're then going to very easily fix most of those. Because most of these, all that needs to change is we add dot value. So I'm going to fix the predicates first, because those are the main things that I want to illustrate. So just all of these get dot value. But we're not changing really the actual sort of structure of the code. Structure of the code remains exactly the same. All that we're doing is making some minor modifications to how it retrieves the data for it. And we just need to do a similar thing here with the iterator. These are just slightly different because these are working with the iterator itself. So apart from that, well, let's run it. And everything still just works exactly the same. Nothing's any different there. So we can use it with integers, we can use it with a more complex type like this where it's a structure. The actual algorithm stays the same, we just need to make minor modifications to the predicate to work with the particular data. And generally what you'll see is if the type that we're iterating over, the container is holding one of our pod types, so int, float, something like that, you'll generally see the predicates take the data in by value, which is what we originally had. Where it is something where it is a complex type, right, so it's a structure or a class, something that's sort of larger, heavier weight, where we don't want it to be creating copies, then const reference is more what we would expect to see here. Likely could just use a general reference, and we can test if that actually works, which it does. By value would also still work, but it's going to be creating copies there, potentially where we shouldn't actually be creating them. So we generally want to structure our code so it's as safe as possible. So when it can be const references, we should be using const references, or a const pointer if it's pointer data. Because we don't want to be modifying this, we don't want to even have the remote chance of modifying it inside that predicate. So highly recommend, if it's simple value types where it's safe to create a copy, pass by value. Otherwise, const reference, const pointer, depending upon what's going to be most appropriate for the data that you're working with. But this gives us our intro to some basic sets of the algorithms. Like I said, I will place a link in the description to the larger list of more of the algorithms that are available. There are a lot of different ones. A lot of them follow a fairly similar structure to this, where you can be providing a predicate. I am a big fan of the predicate-based setup, just because I'm often processing data where I need to actually use, it's not enough to just have one way of sorting it or one way of finding things in it. I often need to have multiple ways of doing that. So predicates allow me to use the most appropriate method for that particular scenario. But dive on in and experiment with this. Set up some more complex data yourself. Add in different values here. Add in different criteria for it actually doing the comparisons. And see what you can come up with. See what you can break. Again, want to be breaking lots of things because you're going to run into errors no matter what. You're going to break things no matter what. So you might as well do it early and intentionally, and then be able to be learning from it, rather than having those errors and that breakage happen at a point in time where you might be trying to get something working urgently. So dive on in and experiment. Thanks folks, hope you found the video interesting and helpful. If you have, chuck in a like and subscribe, it really helps out, it's really appreciated. If you've got any questions, chuck those in a comment below. If there's other ones you'd like to see me cover, then mention those also. If you are looking for the code for the project, there is a link to that in the description. It is available up on GitHub. All of the code you're able to use in any of your own projects, commercial or non-commercial ones. It's freely available for being used there. And if you are looking for other ways to support the channel, then I do have a Patreon, and there is a link to that in the description as well. But until next time,